Hey guys, we're here to talk about free body diagrams. So this is something that you saw a little bit of actually, and I think he mentioned it as well in the video talking about the common forces. You should have already taken some notes about that. It's the picture we need to make to break down all the forces that are acting on an object. So a free body diagram, or an FBD, I'll call it. It labels all the forces acting on an object and, more importantly, their directions. Remember that force is a vector, which means it has magnitude, how hard the force is acting on something, as well as direction. Because if I'm pushing in this direction with a force versus pushing in this direction with a force, that's very much so going to affect the motion of my object. So we have to be very careful with noting our directions when we're talking about forces. If we're pushing on something at an angle versus pushing on it straight on, we're going to talk about all those things, and a free body diagram helps us break down all those different forces acting on an object. Now, the way we draw these, you can obviously, if you're an artist, you can draw the object itself. Typically what I do is, no matter what the object is, I usually draw it as a square. Depending on the situation, maybe a circle. But either way, we draw all forces coming from the center of mass of the object. So wherever what our object looks like, we draw it coming from the center of its mass. So obviously if it's a square, it's the literal center. If we're talking about a person, center of mass is like right from our stomach. That's our center of mass. So we just draw all of our vectors starting at one point. They all come from the same point. Now, once again, we're going to be looking at all of these different forces, which we've already talked about, and labeling them on an object. There is one more also that occasionally we will have. There's a question that asks about it later. Air resistance is a thing as well. It's like the friction due to air. A lot of times they say ignore it because usually it's negligible and it can be ignored unless you're like in a hurricane or something like that. So typically, unless they are talking about it, we pretend air resistance isn't a thing. But in one of these questions, I believe in this lesson, it does bring up air resistance. So I did want to bring that up. So all we're going to be doing this is why this is a really quick Edpuzzle, is drawing these free body diagrams. So a book is sitting on a desk. We want to draw the diagram of the forces acting on the book. So when something is laying on top of a surface, right? We have two forces at work going on here. Of course, for anything, for everything, force of gravity is always there. If here's the center of mass of my book, the force of gravity is pulling it down. Yeah. So do not forget, on every single, unless we happen to be in space, but very rarely do we have questions like that, on every single free body diagram, force of gravity will always be there because gravity is always acting on us. However, hopefully you recall this from the force notes. If I had the force of gravity pulling down, we have a second force as well. Gravity pulls down, but what happens with the table is the table exerts an opposite but equal upward force called the normal force. So this again, they talked about. The normal force is always perpendicular to the surface. So since my surface is flat, this is what we call the normal force. And in this case, my normal force and my force of gravity are opposite and equal. This is something we're going to talk about again in a different lesson, but they are pushing each other away. Yeah. So I'm going to make a little note here as well. This is my free body diagram. This is all the forces acting on the table, on the book. Gravity pulls it down. Normal force, though, is the table pushing up against the book. So a little note here that the force of gravity equals the normal force in this case because we're laying on a perpendicular surface. We're going to talk a little bit more about that later. So that is the free body diagram. And also, again, just to make a note here, they are equal in magnitude, but also opposite. So if we want to label the normal force as positive, the force of gravity would be a negative force. They are in opposite directions. Positive force, negative force. Or you can flip it. It doesn't matter. Remember, you get to choose what you want to call positive. As long as you're consistent throughout the problem, then you're fine. So that's it. Let's go ahead and look at another one. A ball is rolling on a carpet and slowing down to the force of friction. Draw a free body diagram. So to start with, again, we're on Earth. What is always acting on every single object on Earth? The force of gravity. So I always draw that first because it's always a thing. Here's my force of gravity. And again, I'm going to call that negative because it's pulling down on the object. But again, if we have the force of gravity pulling us down, there is a force acting perpendicular to the surface, which in this case, if the ball is just like this, perpendicular to the surface is just going to come straight up. So it's going to be opposite gravity. What is that force acting perpendicular to our surface? The normal force. Here's my center of mass. There's my normal force. Once again, I need to be clear that the normal force is not opposite gravity. It is perpendicular to the surface. It just so happens that for right now, we're talking about flat surfaces. So it is opposite gravity in this case. This is a true statement. Whoa, sorry, that's supposed to be a subscript. F sub n. This is only a true statement right now because our surface is flat. Later, it's not necessarily true. Now we do have another force though, because it is slowing down due to the force of friction. So if it's rolling along the carpet this way, it's going this way, right? Phew. Think about which way friction is acting on this ball. Is it pushing the ball forward or is it pulling the ball backwards and slowing it down? So take a second to think which, it's going to be either off this way or off this way. Which way do you think the force of friction is acting on this ball? Okay, so hopefully you can see that the force of friction, I'm going to call this negative, is acting opposite to the ball's path. If the ball is going this way, friction is pulling against it, which is what causes the ball to slow down. So the force of friction, make a note to yourself there. Force of friction acts opposite. Though this is something you probably do have written down anyways, but just in case you don't, if you didn't write it down when you talked about when you did the forces video, acts opposite to the direction of travel. That should make sense. That's why things slow down when they're in contact with surfaces that have a lot of friction. It acts opposite to the direction you're traveling. So there is our free body diagram. We've got gravity and the normal force, but we also have friction acting against it. So it's very important to know what our direction of travel is. Okay, so this one now, we have a ball dangling, yeah? So, little hint here. The ball is not on a surface. We do not have a normal force. You only have a normal force when an object is in contact with a surface. So normal force is not going to exist here. However, we are on Earth. What force is always on us? Gravity. So to start with, once again, gravity will always be pulling down on us. So that force always exists unless they happen to say we're in space. I'm pretty sure we don't have any questions like that though. But like I said, we don't have a normal force because my ball is not in contact with something. What we do have is an object dangling from a string. This is a different force, one of the 5 that we talked about. Which force do you think we're going to be dealing with here since I have something pulling against a string? This is called the tension force. The ball pulling down with the force of gravity is causing tension on that string. So again, on that ball, it's going to feel the tension of that string. That force is actually acting on the ball. So instead of the normal force here, we're going to have the tension force. Sometimes you see this as Ft. Sometimes you just see it as T with like a subscript sometimes for different different tensions, like different amounts of tension. I'm going to go ahead and call it force T, force of tension. And again, what we see here is that in the same way as the normal force, because they're pulling in opposite directions and the ball just hangs there. Because the ball is just hanging, what this means is the force of gravity equals the tension force as well. Because if the ball is staying still, it's not moving. What that means is there is no net force acting on the ball. If something is at rest or it has a constant velocity, we're going to make sure we understand that, there is no net force acting on the ball. If I were to add these two forces together, we would get a zero net force. So once more, if something is at rest, that means if I were to add the forces together, we would get zero, no net force. Okay, from here, we're going to bring it back and we're going to go through these next ones together because they're a little bit trickier. Yes, we're going to go ahead and do that. So finish this video up and bring it back to the WebEx and we're going to keep going from here.